Now we're going to talk about Dijkstra's algorithm. Dijkstra, who is a Dutch mathematician, computer scientist, came up with what is now perhaps one of the most famous algorithms in computer science, and it's kind of a cool algorithm. What Dijkstra's algorithm does is it finds the shortest path distance from every node in a graph to some given root node. It works on both directed and undirected graphs. It runs in time O of n plus m log n, where n is the number of vertices, m is the number of edges. And it requires this data structure that we're going to talk about called min-heap. We'll get into that. At a very high level, what Dijkstra's algorithm does is it maintains a few different data structures. It maintains this dictionary or array called distances. What distance is doing is measuring a current estimate of the distance from the root node to every node v. This will be initialized at infinity for every node that isn't the root node, and it'll be progressively decreased. The values and distances will be progressively decreased as the algorithm iterates. Dijkstra also maintains this, what we'll call the v-scene array. V-scene are the vertices in the graph that have been found by Dijkstra's algorithm, and where we have an estimate for the distance that's less than infinity. But these distances are not necessarily correct yet. We're not sure if we've correctly computed the distances in v-scene yet. V-done will be vertices, which we're sure we've already computed the optimal distance between the root node and v for these V-done vertices v. And V-done will essentially be the vertices that were already added to this heap V-scene. V-scene is going to be a heap data structure. They were added and removed. So if you were in V-done, it means you were added to V-scene and then later removed from V-scene. V-unseen are the vertices which you actually haven't encountered yet. These are the vertices which have an infinite distance and they haven't been added to V-scene just yet. So we're going to maintain these 4 different categories and 4 different data structures. Mostly we're going to use just distances in a V-scene heap. V-done and V-unseen will be inferred from the items that have either been added and removed from V-scene, that's V-done, or V-unseen, which are just the items that haven't been added to V-scene yet. So keep your eye out for primarily these 2 data structures right here. We should look at the code for this algorithm so we can see it up close. Here's some code for Dijkstra's algorithm. I want to note that we're going to be using this thing called a heap. I actually stole some code from the internet, which implements this heap dict data structure. There is a heap data structure implemented in Python, but it actually doesn't have one operation that I needed, and it's an important operation. So I found that there's this implementation that includes that operation. I'll talk about that in a moment. What this Dijkstra algorithm does, it takes in the vertex set and the edge set and a given root node, and that's how it starts off. These edges, the edges E, are going to be the weighted edges. It's going to contain both, for every vertex, it's going to contain both the neighbor index or the neighbor vertex along with the length of that vertex. So every edge has an actual length associated with it. Okay, so what this Dijkstra algorithm does is it initializes this distances array, this distances dict, and it starts off as being infinity for every vertex in the vertex set. It actually initializes the root distance to be 0, right? Because this distances dict is supposed to store some estimate of the distance from the root to every other node in the graph. Initially it's infinity, but for the root node that distance is going to be 0. So you're going to create a heap dict data structure for v-scene. These are the nodes that have been seen so far. It's going to be a heap dict data structure. You're going to add the root to this data structure. This is just a way of saying that the root of the graph is going to be added to this heap with priority value 0. Okay, so then the while loop of Dijkstra's algorithm checks to see if there's any more nodes left inside of the heap, inside of v-scene. These are the observed nodes thus far. It pulls out the current vertex, a vertex from the heap, and the distance associated with that vertex, which is the current estimate of the distance from that vertex to the root. And it uses this very fancy operation here, which we're going to talk about, vdistance heap.pop item. What that pop item is doing is it's taking the smallest item, the item in vscene, this vscene heap data structure that has the smallest priority value, which is going to be set in calls like this. It's actually, most of them are set down here. So it's pulling off whatever items have been added to this data structure, but have the smallest priority value. Okay, so now that it has the smallest, the vertex with the shortest distance, the priority is going to be the distance. It pulls off this, it pops off this vertex in the heap with the shortest distance, and it is going to now run through the edges attached to this vertex. It's going to look at the length of every edge, and it's going to add that to current distance. This is this current distance is the current estimate of the distance from the root to the current vertex. And for this neighbor, it's going to suggest that there may be a shorter distance. This distance is a potential better path than the one that has already been found to the neighbor. You're going to propose that there is this new shorter distance, which is current distance to the current vertex, plus the edge length, plus the length of the current edge. And if that distance is better than the current estimate we have for that neighbor, if you've actually found an improved distance, then we're going to update the shortest path length from root to neighbor with this distance value. And then we're going to make sure we incorporate that new distance into the heap. We're going to make sure that this vscene has an updated value for this neighbor using this shorter distance. So it may seem what we're doing here is very simple. We're simply updating a value, but it turns out a value in this vscene array. But it turns out that this operation is actually very subtle. We're using this heap data structure. There's two operations that take on the order of log n. First, you have to call the pop item call, which gives you essentially the lowest priority element of the heap. And you have to then do this decrease key or insert operation, which also takes in the order of log n. So why these take log n is going to be something we'll discuss later on in the video. So just hold off onto that. The choice of this data structure is very subtle, and we're going to get to that. Let's now look at Dijkstra in practice on a particular graph. Here, this is a graph on 5 nodes. We have A, B, C, D, and E. We have these edges here marked in light blue with the weights marked in blue. And we initialize this distances array that'll be in red. The distances array will be in red for every single node. We initially start out with every node having a distances value of infinity, except for the root node. Let's say A is the root node. It has a distances value of 0. So what we're going to do is we're going to initially add node A to the queue, or to vscene. We're going to add it to this heap data structure. So what we'll do is we'll mark this with a little star. And now that it's been added to the vscene heap, we're now going to pop whatever the minimum distance value is off of the heap, and we're now going to look at all of its neighbors. Okay, what are we going to do for every neighbor? We look at the edge weight associated with each neighbor, and we compute some distance value to the root. In this case, we're going to look at first neighbor B, and we're going to say, okay, what is a potential distance, new distance from root to B? Well, we take the distance value here to A, which is 0, because A is the root, plus the edge weight, which in this case is 2, and we say now we found a path from A to B, which has value 2. Is 2 smaller than infinity? 2 is smaller than infinity. So we're now going to take this infinity, cross it out, and put the number 2 here. And again, that 2 came from the fact that we had 0 as the distance and 2 with this edge weight here. And now we're going to add B to the queue. We mark it with a little star. And let's now go on to the next edge of A. In this case, that edge is that next node is going to be C. We look at the distance from A to C. That's 1. The distance from A to the root is 0 because A is the root. So we're going to notice that 0 plus 1 is less than infinity. So we're going to cross out this infinity, write down the number 1. And mark this thing with a star because now it's in vscene. A can now be marked as done since we've processed it. So I'm now just going to put a little yellow mark over A to say that it's done. Okay, now we look back at our vscene heap. There's two elements in vscene. We have to ask which one has the smallest distance, which is the smallest distance value in vscene. The smallest distance value is going to be C, because C has current distance 1. We've crossed out this infinity here. We're going to pop that off of the vscene heap. Let's now cycle through the neighbors of C. C's first neighbor is B. So now we're going to consider, is a path from B to the root going through C better than the current estimate of the distance from B to the root? Well, currently we know that the distance to C is 1 because of this red value here. The edge weight between B and C is 2. 1 plus 2 is 3. And we ask ourselves, is 3 better than 2? And it turns out 3 is not smaller than 2. So we do not update the distance value for B. We don't do any update for this B distance value because 1 plus 2 is not a better path than the direct path from A to B. So no updates are done for B. Let's now go to D. We again look at the edge weight from C to D. That's 3. We add that to the distance estimate for C. That's 1. Is 1 plus 4 smaller than infinity? Indeed it is. So we cross out the infinity and we write down 4. 4 again is 1 plus 3. We now have an updated estimate for D. We also add that to vscene by marking it with a green star. Finally, C is connected to edge E. We take the distance 1 for C, we add that to the edge weight 1, and we ask ourselves, is 1 plus 1, or 2, is that smaller than infinity? And it turns out that is smaller than infinity, so we cross out this infinity, and we write down 2. And we're going to then add E to the vscene heap. Okay, now that we've looked at all of C's neighbors, we can mark C as done. C is now going to be done. We're going to mark that as yellow. We now look at what is remaining inside of the vscene heap, and we take the smallest value in the vscene heap, smallest value in terms of the distance array. Well, it turns out that there are 2 nodes with distance 2 that have 2 marked in red, so I can pick either one of them. Let's now pick node B. So we're going to look at node B, and we're now going to start to process node B. Let's now look at all of B's neighbors that are still in vscene, that are not marked as done. We're going to skip over anything that's marked as done. B's first neighbor is, let's say, D. It's its only neighbor remaining that's not marked as done. And we ask ourselves, is the distance from B to the root, which is currently estimated as 2, is 2 plus 3, which is this distance from B to D, the weight of the edge from B to D, is 5 better than 4, 4 being the current estimate of the distance for D. And it turns out that this path, 2 plus 3, is not better than the path 4 that we already have. 4, of course, came from the fact that we could have gone first to C and then from C to D. So we actually do not update the distances value for this node D. We leave it as it is. That was the only node that B is connected to that isn't done. So we're done processing B. We mark that as yellow. B is now done. Now again, we have a vscene heap with 2 items in it, D and E. We take the one that has the smallest distances value. That, it turns out, is E. We pop that off of the heap, the vscene heap, and we now consider all of E's neighbors that are not yet done. So currently, E has only one neighbor, that is neighbor D, and we ask ourselves, is the distance 2, which is E's current estimate of the distance to the root, plus the edge weight 1, is this a shorter path than D's current best path, which is 4, right? This is D's current estimate of its best path, which is 4. And it turns out it is. 2 plus 1 is less than 4. So we now erase this 4 and we write 3, because that's a better path. E has no more neighbors that aren't done, so we mark it as done. We now proceed to look at the heap again, the vscene heap. We pop off the only item left in the vscene heap, and that is node D. We notice that D has no neighbors that are not done yet, so we can conclude that 3 is the shortest distance from D to the root node A. So we're going to mark this as done. So now we have all of the shortest distances for the entire graph to node A, and we can be sure that that is the correct shortest distances. So there's a question about why Dijkstra actually works to compute shortest distances from all points in a graph to the root node. This is actually a difficult thing to prove. I'm going to give you a bit of a sketch of how the proof works. You essentially do what's is a proof by induction. You're going to show that the following two facts are true after every iteration through the while loop of Dijkstra. Every time you process a node, you pull it off of the heap and you process it by looking at all of its neighbors. At the end of that loop, you're going to find, at the end of the iteration of that loop, you're going to find that two facts are true. First is that there's some value D which separates all of the nodes that are in VDone from all of the nodes that have either been seen yet or in VSeen or have not been seen yet. So essentially there's a separator distance D from the root. All nodes that are closer than D to the root are going to be in VDone, and all those that are not as close as D to the root are going to be in either VSeen or VUnseen. That is going to hold true on every iteration of the while loop of Dijkstra. Also, for every node V, distances of V is the length of the shortest path from the root to V, whose intermediate nodes are constrained to be in VDone. Essentially, what you're doing is you're increasing the size of VDone on every loop, and what values you're seeing in distances for all the remaining nodes, those that are not done. The value for distances of V is going to be the length of the shortest path that has to go through VDone, that first connects to a node in VDone and then takes the shortest path from there. These two facts have to be checked carefully. I recommend that you think about on one iteration of the loop, the Dijkstra while loop, and why you would expect these facts to hold true. But you can prove this very formally, and if you think about this carefully or have a look at the book, you'll see a precise explanation for why these two invariants are maintained through every iteration of the while loop in Dijkstra. So let's think about the running time of Dijkstra. You'll notice that we had to encounter every single vertex in every iteration of the while loop of Dijkstra. We observed a vertex, and then we started looking at all of its neighbors. Whenever we pull off a vertex from the VSeen heap, that takes on the order of log n. I'll talk about that in a moment, why it takes on the order of log n. Whenever you pop off this vertex from the heap, you then look at all of its neighbors, and for every neighbor, you look at the vertex associated with this neighbor, and you either have to add it to the heap because it wasn't added to the heap before, or you have to decrease the distance or priority value in the heap, which also would require on the order of log n. These are specific details of the heap data structure, and we'll talk about that in a moment. But you'll notice that you had to do an O of log n operation every time you encountered a node or an edge in this graph. Therefore, for every node and edge in the graph, you had to do an O of log n operation. So the total running time of Dijkstra is going to be on the order of O of n plus m times log n. So I kept emphasizing that we're going to use this heap data structure. I'll link to another video that describes how you produce a heap data structure. It's an interesting data structure that stores all of its data inside of a binary tree with a very particular property that needs to be maintained for that tree. Watch the next video to get that. But the question is, why don't I just use some simpler data structure like a list or something like that? Well, it turns out that you want to be able to maintain a prioritized list of items or collection of items and always be able to take the one with the smallest priority value off of this data structure, off of this queue, and then when I get new elements, I can insert them quickly or decrease the value, the priority value associated with that item. And it turns out that that's actually not easy to do. You want to be able to do this in as fast as both this operation and this operation in as fast a time as possible. And it so happens that the min heap data structure lets you do both of these operations on the order of log n. Both this adding, inserting, or decreasing operation, or this popping from the heap operation. Both of these are going to take on the order of log n if you use a very carefully constructed data structure, and that's the min heap. So take a look at the next video to get more details on that.